So we'll now turn our attention to motivating the development of the concept of entropy and stating the second law of thermodynamics. And to that end, I want to call your attention to a class of processes that we call irreversible processes. And I'll define that by example here. So let's say you have a teacup that is precariously perched on a ledge. And what will happen is it'll fall off the ledge and hit the ground and smash into a zillion little pieces. And those pieces will go flying everywhere. Those pieces will eventually collide with the air molecules doing work on them, increasing the thermal energy of the air. So the teacup falls, shards go flying, the room heats up just the tiniest little bit. So we see that one. Now, there's absolutely nothing in the laws of physics that prohibits the reverse process. So we can have a whole bunch of, we can imagine a room that had a whole bunch of teacup shards in it. And the air molecules in the room hit the teacup shards in just the right way that the temperature of the room drops very slightly. We reassemble a teacup perfectly. And that teacup winds up flying back onto the ledge and sitting there precariously perched on the ledge. So, looking at these processes here, both of these are absolutely fine by the laws of physics. So, does the laws of physics say it's okay? For both processes, the answer is a resounding yes. Now, the logical follow-up question is, do we ever actually see it? Well, you've probably seen a broken glass or cup or two in your life. But I am willing to bet a fairly large chunk of my paycheck that you have never seen teacup shards just spontaneously reassemble, weld into a perfect teacup with no flaws, do 1 1/2 flips, and land back on the ledge. So this was a conundrum for physicists, and it actually ties into some other issues, which is that it seems like time has a direction. After all, we remember the past, but we don't remember the future. It's one of those things that seems so blindingly obvious that we don't even state it, but the question is, why don't we remember the future? And that seems to be tied in with this. It seems there are certain processes in nature that, even though there's nothing wrong with it according to the laws of physics, we never actually see them happen. So a way to try to quantify this would be to invent a variable that gets bigger as these irreversible processes occur. And the name of this variable is the entropy. The usual symbol for entropy is a capital S, and it'll turn out that the units of entropy will be joules per Kelvin. And so then what we'll have is, for a closed system, what we'll want is the change in the entropy of the system to increase if it's irreversible, and we'll have equality only if the process is reversible. Alrighty. So let's go ahead and start to try to define this. So the idea being, If some irreversible process occurs, we'll know that that's the case because the entropy went up. If it's reversible, it'll be 0, and we'll not have negative changes in entropy because that would be the same difference as, say, being able to remember the future. So we'll go ahead and define entropy, but for now we'll only define it so far as its change. We will then link it in statistically in the next video, where we'll be able to define it absolutely and not just simply to it within by its change. But for now, we will define the change in entropy of a system to be the integral of the heat transferred over the temperature, going from our initial to our final state. And I threw that little slash into the D because technically, since heat is thermal energy in transit, it doesn't make sense to talk about a true differential. So the bar is something that physicists do when they remind themselves that they really do have to treat this as a really tiny delta, and the integral is really a sum over a lot of little tiny heat transfers. So anyway, our goals here are that if this is the right thing, then for an irreversible process, delta S will be positive. And the other thing we want from this, and we'll be able to get it, is we want the entropy to be a state variable. So that seems pretty fancy, but what this means is that delta S will depend only on the initial and final states of the system. And not the thermodynamic processes used to get there. This is analogous to when we defined potential energy. Potential energy only depended on the forces involved and the configuration of the system at the beginning and at the end, without any concern about the actual path that the object took. This is the same kind of idea. We're only going to care about what our initial and final state of the system is without caring about how we actually got there. Now, there's a really good reason why we want that, and that's to remember that for a typical process, if I draw a PV diagram for it, literally all I can do is draw the initial and the final position, and we just have to put a big I don't know for how we could ever possibly connect those two states. So we definitely want to just depend on the processes. Now, let's say that just by sheer happenstance, these two states happen to be at the same temperature. So this dotted line here would be an isotherm. So even though there's no way that I can really connect the one to the other, we don't know, in a typical case, we can't even draw a PV diagram. We can only just draw the initial and the final state. Since entropy only cares about what the initial and final state are and not the details of the process, what we can do is we can go ahead and calculate the change in entropy for, in this case, would be an isothermal expansion. So we'll calculate for our isothermal expansion even though we can't draw the PV diagram for the actual process. And this is okay because entropy is a state variable. So the entropy here will always be S final, no matter what it is, and this will always be S initial, no matter what that is. Well, for this one, we can actually go ahead and calculate the change in entropy, even though we have this really dicey integral that's not really an integral. So we say it's the integral from initial to final, d bar q over t. Now here, because it's isothermal, the temperature is a constant. We can pull that out of the integral. And we're just left with evaluating that. Now this we can look at and say, oh, this is small transfers of heat, and we're adding it up over the entire process to get the overall heat transfer. So that fake integral, which is really just the sum of a lot of tiny delta q's, is just q, our total heat transferred. So for an isothermal process, it's q over t. And if you have a small temperature change, you can approximate the change in the entropy as being the heat transfer over the average temperature you had during the process. So, all right, that's cool. We know what to do if the two temperatures happen to sit on an two states happen to sit on an isotherm. And we even know how to fake it a little bit if they're almost on the same isotherm, but not quite. But how could we go ahead and do this in general? Well, to do it in general, we can think about one more process. And so I'm going to put this here as a pause and ponder moment for you. So if we had an adiabatic process, what would be the change in entropy for that? Pause the video and get back with me. Well, if we go back to our definition here, delta S is integral initial to final of the heat transferred over the temperature. Well, in this case here, even though the temperature is continuously changing, there is no heat transferred in an adiabatic process. So this is just equal to 0. Oops. No heat transferred. All right, so what does that get us? What that gets us is we now know how to find the change in entropy between any two states. So let's say we have two states that do not fall on an isotherm, so P, V. So here's my initial state. Let's just say for the sake of argument, it was saying at a higher temperature, although that doesn't really matter. And then we'll say that our final state was sitting at a lower temperature, even though, again, that doesn't really matter. So the deal here is if we go ahead and find the adiabat that goes through the final like this, we can calculate the change in entropy by first thinking about an isothermal expansion, or depending if the temperature, if the volume were decreasing, it'd be a compression. followed by an adiabatic expansion. So here, for this leg of it, the change in entropy would be the heat transferred in that leg of it over the temperature there. And for the adiabatic expansion, the change in entropy would just plain be 0. So all we have to do is find the connection point. Then we can calculate change in entropy for the isothermal expansion, followed by change in entropy for the adiabatic expansion that connects the 2 points, or possibly compressions. So with those two, even though the real world situation is I can never draw it, and even if I'm thinking about ideal processes that don't look like isotherms or adiabats, I can always go ahead and calculate the change in entropy by connecting an isotherm to an adiabat. So as a quick example of that, let's go ahead and try doing an example here where we find the entropy change for a free expansion. So let's go ahead and say that I have 1 mole of an ideal gas, and I'm going to go, and I have a little membrane here, so we'll say that the volume here initially is V, then Scotty just beams the membrane away. And so now our 1 mole will occupy a volume of 2V. All right, well, there's no heat transfer during we saw for a free expansion, there is no change in thermal energy. There's no, we haven't changed the average kinetic energy of any of the particles. By the first law, that has to be equal to Q plus W. So we can get that the heat transferred in will be the negative of the work done on the gas. And the work done on the gas in isothermal expansion will be nRT times the natural log of V final over V initial. So remember, I'm choosing to do this, to calculate this, to get the heat transfer here. I'm just thinking about an isothermal expansion because the temperature hasn't changed, even though the real process is not an isothermal expansion. So then the change in entropy will be Q over the temperature. So this will be nRT times the natural log of V final over V initial divided by the temperature. Boop, boop, like that. So the change in entropy will be nR times the natural log of 2V over V, which is the natural log of 2. So this is 1 mole times 8.31 joules per mole Kelvin times the natural log of 2. So 1 mole. There we go. Cancel, cancel. This works out to be 5.76 joules per Kelvin. And since it's greater than 0, this is doing what we want. A free expansion is an irreversible process. There's no way we can draw a PV diagram for it. And we see that the entropy change is positive. Alrighty. So our next question here then is, what would be the change in entropy for a closed system undergoing a reversible process. Well, if the system is closed, any heat flows that are happening within the system are going from one part of the system to the other. And since the process is reversible, this means we're obeying the quasi-static process assumption at all times, which means that we have a well-defined temperature. And so this means, and since the heat lost by one is equal to the heat gained by the other part of the system, since the temperatures are the same and the heat transfer is the same, one of them will be positive, one of them will be negative, we might see the entropy of one part decrease, but the entropy of another part of the closed system increase. And it would be by the same amount. So we would get that the change in entropy is zero if the system is closed and undergoing a reversible process. So this gets us to our first form of the second law of thermodynamics. So the second law of thermodynamics will say that for all closed systems, for a closed system undergoing any process, so for a closed system, and this includes the universe itself, is a closed system, the change in entropy is positive semi-definite. So greater than or equal to zero. We'll have the greater than sign for any real world process, and we reserve equality for a reversible process. So what do we get out of that? We actually now do have an arrow of time. It's actually one of several arrows of time that we have found. There are various things in the universe that help, the various things that happen in the universe that point in the direction that time flows. This is one of them. Time flows in the direction of increasing entropy. And so this actually explains why we remember the past but not the future. So in order to make a memory, you're going to have to organize your brain somehow. This is going to involve expending energy. That energy is going to go off as heat. So in order to form a memory, you wind up causing the air molecules around you to get heated up. And the entropy change in those air molecules is greater than any decrease in entropy that happens from your brain organizing itself a little bit. So you wind up, so it turns out that in order to make a memory, you have to increase the entropy of the universe, which is our closed system that we're thinking about here. So that, therefore, you remember the past but not the future, because if you're going to remember the future, then that would be a process, then you would be able to reverse the process and have a decrease in entropy of the universe, which would violate the second law. Now, we've got more, as is always the case with with these laws of thermodynamics. So we'll note that we have an arrow of time. So we'll say that time flows in the direction of increasing entropy of the universe. To give you an idea, some of the others, another one is time flows in the direction of the asymmetry of the decay of a subatomic particle known as a neutral kaon, just to show that entropy isn't the only game in town for this. but all the arrows of time point the same way. So give a couple more statements of it. In a later video, one of them that we will show is that no heat engine can exceed what's called the Carnot efficiency. And it's spelled like it was Carnot, but it's Carnot. Let's put that together at the end here. C-R-N-O-T. So it's pronounced Carnot efficiency, which is the most efficient possible heat engine that we can make. So we'll demonstrate this in a later video. But we'll use that result right now to argue that heat cannot be spontaneously transferred from a cold object to a hot one. Which is another statement of the second law. You can move heat from a cold object to a hot one with the input of work. We'll talk about that in a later video. But we're talking just purely heat transferring spontaneously from something cold to something hot. We've already seen this when discussing a bit the zeroth law of thermodynamics. We saw that heat transfers happen because of collisions between atoms, and the atoms with more thermal energy will lose energy to the ones with less. So this makes sense. But again, it's why don't we have it where you have everything just happen to go the other way? It's theoretically possible, but we don't see it. So using this statement that we get from the next video, or sorry, in a later video. If I try to draw this graphically, the way we usually draw heat engines is we imagine connecting two reservoirs. And a reservoir is just something where the temperature won't change appreciably with any addition or withdrawal of heat. And the heat engine itself usually gets drawn as a circle. And what we're saying is we'll pull heat out of the hot reservoir, Q cold, reject it to the cold reservoir, reject it to the hot reservoir. And although I can draw that process in a heat engine diagram, the second law of thermodynamics says that this doesn't actually happen. And here's a sketch of how to prove that. So we'll imagine connecting our hot reservoir and our cold reservoir. Now, a way that I could create a device that would encourage this theoretical spontaneous flow would be to take a Carnot engine. It would pull heat from the hot reservoir, we'll say Q hot engine, and we'll see that it'll have to reject some, when we come up with the Carnot engine, we'll see that not all the heat can be turned into work. So we'll reject some heat to the cold reservoir and we'll extract useful work out from it. Then we'll hook up another heat engine here and run it backwards so that it acts like a refrigerator. So we'll be pulling heat from the cold reservoir with the refrigerator and rejecting some amount of heat to the hot reservoir from the refrigerator. Now, if I want to so if this is a Carnot engine, this is a Carnot engine, it all just cancels out, and it'd be the same difference as if I never connected anything at all. But since what I want is a net upward transfer of heat from the cold reservoir to the hot. What I'll need here is a heat engine that's better than a Carnot engine that we run backwards to be a refrigerator. And the second law of thermodynamics says that no heat engine or refrigerator can be more efficient than the Carnot cycle. So you can't build it. So since you can't build this, you can't have that happen. Now it is entirely possible with the addition of outside work to move heat from something cold to something hot. That's how your refrigerator at home works. But to just have it spontaneously go, that's something that can't happen. All right, so in the next video here, we're going to go ahead and turn this around a bit and look at Boltzmann's statistical formulation of the second law of thermodynamics. So we'll see you over there.